start, I would like to thank the chairperson, Professor Swadim Mandal, and then Academy for giving this platform to showcase few of our research work and what we have been doing at IISER Tirupati, how our research contributions helps for the sustainable development. And most of the industrial processes are mainly dependent on catalytic processor. Over 90% of chemical which the industry produces is based on catalysis, right? And most of these catalytic reactions are, we have to depend on precious metals, for example, palladium, ruthenium, rhodium, iridium, etc. Now, but ultimate aim is to replace those metals by a metal-free catalytic system. Professor Swadim clearly explained how group exploited a metal-free catalytic system for various synthetic transformation. But that's in the futuristic thing, because we have to go long way to make the things sustainable. And now that presently we are in an era to replace the precious metal catalysis by non-precious metals. Particularly we are working on manganese, iron and nickel. And how one can use these non-precious metals for a various synthetic transformation. So both the speakers are discussed about how one can use the carbon dioxide for the production of various important compounds, including fuels. Now I'm going to touch upon few things, and based on non-precious metal catalysis using alcohols as well as the CO2. These two are fundamental feedstock chemical for making various interesting compounds. And my first talk I will be discussing about how one can utilize alcohol as a sustainable feedstock for making various chemicals. And second, we will also touch upon hydrogen generation from waste material, and finally CO2 to polymers. And you look at this slide. By looking at this slide, it reminds us as people wearing the mask is a COVID situation, but this is not the one. So what they are doing is they are trying to dispose the chemical waste produced by the various industries, particularly pharma industry. This is a place called a Valley of Drums in Ketsuki, and you see that so much of chemical waste was dumped, and these two gentlemen trying to dispose this. But there's a proverb called prevention is better than cure. So before producing this, you should before mitigating this, you should come up with a new type of solution how one can avoid the formation of all this chemical waste. So this sustainable catalysis in an affordable chemical manner, this is the one which gives a kind of solution, right? And with that, several world-class companies which are listed over here, they are partner of Organic Chemistry Institute. They had a brainstorming section almost a decade where when I started my independent career. They discuss the reactions that are frequently used in the industries, and they also discuss what is the waste management, how to mitigate those waste and all the things. And these are the reactions which they are routinely using their industries and also produces a copious amount of waste. So one of the reaction, if I look at it, this alcohol activation for amination reaction or CC and CN bond forming reaction paid much attention, but and you see out of 6 companies, the 5 companies they voted, and they need a better solution. Presently what they are doing is they want to have an alternative or better solution. The only solution they prefer is a catalytic manner, how one can activate the alcohol and use alcohol for various chemical synthesis, and based on non-precious metals always is most welcome one, right? And removal of hydrogen from alcohol, this is the way one can activate the alcohol, and it's not a simple process, it's a thermodynamically uphill process, right? And you must require huge amount of energy to remove hydrogen from adjacent molecule of ethanol. So you must require a suitable catalyst design for that to do the dehydrogenation, and we have been working on a catalyst design based on the non-precious metal for this very interesting reaction, that is dehydrogenation of alcohol, right? And why non-precious metals? Obviously all know that it's relatively much cheaper, and very important things are these elements are biorelevant, and if you look at the toxicity level is concerned, except cobalt and other things are relatively toxic when compared with the precious metal which mostly used in the industry for making various chemicals. And however, while working in the non-precious metal complexes, one has to encounter several challenges. What are the challenges? So the metal dissociation is one of the problems. So metal comes out from your ligands. So you have a metal nanoparticles. So it's very difficult to understand the reaction. Sometimes there are not any reactivity. So you must have judiciously design a catalytic system to stabilize this metal center, particularly the 3D transition metals. And also the interconversion between the oxidation state. For example, taking the magnesium, the periodic table, so one of the elements which the oxidation state of this manganese vary from -2 to +7. So 0, +2, +3. So there is always there is a variable oxidation state. So if you want to use it in a catalytic reaction, there should be a discrete electron transfer or this oxidation addition or reductive elimination, which are very common in chemical reactions that would happen, right? And how one can tackle this problem? So you must come up with a suitably designed catalytic system. This is what we have been doing, and here we have designed a catalyst based on manganese. There is a purpose for designing such kind of a rigid backbone. I don't want to go into detail, but what it does is, and typically in organometallic chemistry, basically I'm from organometallic background, the metal center is the only active center. So whatever the reaction you perform, the reaction happens only at the metal center. Right? But if I look at the biological system, for example, several metal enzymes, not only the metal centered, the ligand, the secondary interaction plays very important role. And but making such kind of synthetic molecule is always challenging one. But for a few decades, people have contributed a lot in this particular field, and we are one of them from India, where we have chosen a kind of metal complex. You see, there is a manganese, and this is a de-aromatic in nature. And upon reacting with alcohol, and this alcohol OH1 activation took place, and you see carefully that hydrogen has gone to a ligand side, and then this maintain the oxidation state of the metals throughout the reaction same. This is very important whenever you are working with the 3D transition elements, right? And upon heating, you get back to your complex with the formation of hydrogen and then value added product. And the same complex, upon reacting with the hydrogen, and you get a ring hydrogenated product, you get this compound. I look at it very carefully, and these two are, when you react with alcohol, it behaves like a Mason catalyst. It's an Israeli scientist, where this aromatic to de-aromatic, that's a driving force. And if I look at it in the hydrogenation chemistry, this behaves like a Noyori type of catalytic system who received the Nobel Prize in 2001 for asymmetric hydrogenation of prokaryotic compound. So in a single system, we can have two different metal catalytic system. This helps us to do a dehydrogenation chemistry using alcohol as well as the hydrogenation chemistry utilizing hydrogen for various reactions. And initially we have used this metal catalyst for the conversion of carbon dioxide to methanol. So Sebastian already has a plan for converting carbon dioxide to methanol. This is a heterogeneous system at the technology level higher. And here what you have shown is a fundamental approach. One can convert the carbon dioxide into methanol using this particular catalytic system using amines. So amine is acting as a autocatalyst. How? So initially this carbon dioxide converted to amide, and then followed by hydrogenation you get methanol. Now people talk about the circular economy or circular chemistry. So it means that whatever the waste you are generating, you should bring it back to the same system. That's what Professor Sadim also clearly mentioned. This is also one of the goals which chemists should address, right? And now what you have used is the same catalyst can use for dehydrogenation of methanol. So removal of hydrogen from this methanol. So you get hydrogen. That hydrogen will be utilized to convert this kind of various intermediates or compounds to several other products. Right? Not only this chemistry is applicable for the transfer hydrogenation, you are transferring hydrogen from one molecule to another, and instead of deuterated methanol, if you use, the deuterium incorporation would happen. So deuterated drugs are very important, which has the strong metabolic stability, and many pharmaceutical companies now they are moving towards deuterated drugs. So yeah, our simple chemistry which help us to make such kind of molecule in a sustainable and affordable manner using methanol as a fundamental feedstock. And now I can explain to you how one can utilize this alcohol for making various chemicals. I don't want to go into detail, just I'll touch upon a few things. And you know, alcohol amination is very important reaction. So for example, if I want to do the alkylation, so typically people use alkyl halide, which is metogenic in nature and as well as is a toxic. When you react with alkyl halide, you produce a copious amount of base, acid base, and also the product which is more nucleophilic than your primary amine. So there will be a multi-alkylation reaction. So there is a challenge whenever you work on this particular system. So, but simply you use alcohol. This alcohol first undergoes a dehydrogenation. There will be a removal of hydrogen, and then you get carbonyl compound. There will be a condensation reaction. There is a water, and whatever the hydrogen is liberated, that will be utilized by the same metal complex, the same system. You get the N-alkylated product. So we have shown this reaction and using a nickel-based catalyst. So one of the non-precious metals, and not only the amines, even for example nitro compound. You know, nitro compounds are the fundamental chemical for making various pharmaceutically important compounds. So what you have shown here, simply using a deuterated methanol, so you can hydrogenate. So first this NO2 compound converted into amine and followed by an alkylation. So again, deuterated chemicals, so one of the pharmaceutically important compounds, is very important thing. In a affordable manner we did it. Okay, and also this strategy was extended for diazo compound, and diazo compounds are a dye industry based product. So one can have a value added to dyes also by using a non-precious metal, using alcohol as a hydrogen source as well as alcohol as a alkylating source. This chemistry is not only for C-N bond forming reaction. In organic chemistry, C-C bond forming reaction is one of the fundamental reactions. Also applicable for C-C bond forming reaction, particularly amides, and later this strategy can be applicable for a peptide modification. So what are the peptides are there, using our strategy one can modify, that will have a big impact in synthetic chemistry as well as the chemical biology. And also this is very interesting reaction. The reason is you are taking a two different alcohol which are dependent and feedstock chemical, one can integrate it, one can make varieties of extended alcohol, and later this can be dehydrated and hydrogenated, one can use it as a jet fuel or rocket fuel. And also ethanol to butanol. Butanol is considered one of the biofuel, and we have applied our strategy for making this ethanol to N-butanol. And using our synthetic strategy, like non-precious metal is one way is using non-precious metal. Another thing is alcohol is a fundamental feedstock chemical. We could make varieties of pharmaceutically important compounds as well as several lifelike molecules, right? So both CC and CN bond strategies used to make these molecules. We have used a very low catalyst loading of non-precious metal, and second thing is alcohol as a starting material. And during the course of the reaction, water is the only byproduct. And we applied this strategy for direct amination thing, and these are kind of monomer mostly people use in the polyurethane industry. So the terminal OH was converted into amine, and that is considered as one of the monomers for polyurethane industries. Okay, we have also used a reusable nickel-based catalyst for converting alcohol into amine. And the C bond forming strategy also was applicable to make one of the donors molecule, which plays very important role in Ziegler-Natta polymerization reaction. And Ziegler-Natta polymerization, you must have this particular donor which has a cell limiting or cell extinguishing property. And with this indigenous company, and we developed a synthetic strategy for making such kind of molecule using again alcohol as a fundamental feedstock, and you could make a kind of varieties of proprietary type of molecules, and which really indeed reduces the imports cost from $390 to $98 per kg of this particular molecule. and not only applicable for making a pharmaceutically important compound as well as the petroleum industry relevant compounds like a polyurethane industry as well as and Zirconate polymerization. We can also make several heterocycles, and these are from the chemist perspective. One can have various interesting molecule which has these cores, several pharmaceutically important compound as well as biologically important compound which has these two cores, and one can make this molecule by abundantly available the starting material. So you are taking unsaturated system, means you are taking a saturated system and you are making unsaturated system with the formation of hydrogen gas as well as the water. So in the overall process, only these two are the co-byproducts. And these are some few representative example, and you can have a multi-substituted various type of compound. I don't want to go into detail, but what I'm going to convey here is one can use alcohol as a sustainable feedstock for making various type of heterocycle compound from a simple aliphatic system with the formation of hydrogen gas and water as the only co-byproduct. And these are some recent contribution on making our strategy for various heterocycle synthesis. And these are what I have shown in the first part is how one can alcohol can be exploited or used for several interesting reaction which plays very important role in synthetic organic chemistry. And now in the second part, I will touch upon the carbon dioxide, and already both the speakers gave a brief an overview about why the carbon dioxide utilization is very important. And there they talk about the hydrogenative route. So you must require the hydrogen. So in situ we make a hydrogen, and that used to convert the carbon dioxide into the value added chemicals, particularly the fuels or shorter hydrocarbons and all. What I am going to show here is the non hydrogenative route. So you don't require any hydrogen. That's called carbon dioxide sequestration, and then non-hydrogenated route you can convert into variable or very interesting molecule. So we are very much interested on this polycarbonate diol. So you know these two compounds one can synthesize from a carbon dioxide via copolymerization reaction with various epoxide, particularly ethylene oxide or propylene oxide. One can have these two, and this is very well established process. But the process of making a polycarbonate diol. So in the world only there are three technologies. One is the November based catalyst used, and also the Evonik catalyst based on the bimetallic system with the William Court catalyst, and also Saudi Aroma catalytic system. But making such kind of molecule is always very challenging things. So why this molecule is very important? So if we have this terminal OH, it has a different additive properties, and not only that, this particular process is one of the well-known process. One can incorporate up to 50 weight percentage of carbon dioxide. If you take other thing, it's not that easy, but 50 weight percentage of carbon dioxide theoretically one can incorporate in a single molecular system. That's the reason this process is very important, but it's also such a challenging process. And this once we have this terminal OH, and mostly the polyurethane industry, we just take a polyol and that be reacted with polyurethane, you get the 2-3 minutes, and you can make a polyurethane. But here you are making a different type of monomer, you are incorporating the CO2. So the polymer which you derive out of this, which has a biodegradable property, this is one of the reasons we are more focused on this. And but there are always challenges. You need to work on the catalytic system as well as the several parameters, and also depending on the condition you do expect a different type of polymers also, both alternative as well as the copolymer, block copolymer. And also with respect to the catalyst, both static as well as the electronic property to be tuned. The reason is we have a two system. One is electronic deficient system, that is CO2, another the epoxide is the electron rich system. So in a single catalyst you have to activate both the ends. One is electron rich, another is the electron deficient. It's always very challenging thing. And we have used a zinc, mace and manganese, the bimetallic system, to perform such kind of reactions. And we could get a 43 weight percentage of carbon dioxide in the polycarbonate diol. And also the operational temperature or condition is very mild, and you see it's a simple copolymerization reaction. You add a carbon dioxide to epoxide without using any hydrogen, and we can make a kind of carbonate the terminal OH, which plays very important role in the polymer industry for making a polyurethanes. And the final part, so far I discussed about the homogeneous system. In the heterogeneous system, making a homogeneous catalyst into heterogeneous is always the industry wants because of the reusability and other thing. So pyrolysis strategy is the one which use first the metal complex and get absorbed on the carbon support and pyrolyze under elevated temperature. You get a kind of n-dope material. We use a nitrogen system. And this is very well exploited in electrochemistry as well as the photochemistry, but in the thermal catalysis is very less explored. And we are shown ion-based catalytic system for a heterogeneous chemistry for converting simple amines as well as alcohol to hydrogen. And also we have used this strategy for making a very interesting pharmaceutically important compound. And we have also systematically studied the nature of support and the metal ligand ratio, and several things were studied systematically, and we found that this composition as well as the size distribution and this core shell microstructure is very important for the hydrogen liberation reaction. Okay, and this is very much highlighted by various media. And finally, I would like to thank first of all the chairperson and also the academy for giving this opportunity. And at least I hope I convince you people that whatever the chemistry or related chemistry we are doing, it's definitely will be helpful for the sustainable thing. So the long way to go since I'm a young scientist and we try to contribute for the sustainable development. And thank you for my motivated students as well as various funding agency. And thank you for your patience for listening to me talk. And I'll be happy to take up any questions.
Bimetallic system for your ChemCom paper?
Yes, I mean SNN systems for CC bond forming reaction.
So what advantage you get using a bimetallic rather than a monometallic system?
Yeah, so this is a homogeneous system. So when you make this complex, so you got that's a sulfur system, SNS system, and this monomer is not that stable, so it's crystallized out, or you got the bimetallic system. But the moment you use that catalyst for our reaction, and when the moment you put it in alcoholic solvent, there is a symmetrical cleavage, and then the solvent coordinates, you get a monomer. I mean monometallic system. That's the one is catalyzing the system.
It goes through cobalt 1.
Yes.
Yeah, wonderful talk. I just want to make a quick query.
Yes.
Like for your transfer hydrogenation using methanol, what solvent you would like to use for those transformations, and are they green solvents, or you have some solution for that?
No, we didn't use any solvent. Methanol itself is considered as the solvent as well as a reagent.
Okay.
Yeah, so no solvents.
Methanol can be reused for.
You see, you just take methanol as a solvent there, and then it liberates hydrogen, and that hydrogen get transferred. You don't really record any other solvent.